Hi, everybody. Welcome. I can't tell you how excited I am to be back at Øredev on stage speaking for all of you. Been a 2 years absence, so super excited for today. I'm kind of figured out that I'm the guy that stands between you and lunch. So I will try and keep time at least, so hoping that's good. That would be nice. That would be nice. Doesn't look like it when you're looking at the menu, actually. So, in the next 40 minutes, we are going to talk about barbecue and how to use technology to get the best barbecue. So we will touch on topics like, of course, barbecue, IoT, barbecue, serverless and event-driven architectures, and yeah, did I say barbecue? So this is IoT-enabled smoker for great barbecue. My name is Jimmy, and I will be your pitmaster today. Thank you. So quick, brief look at the agenda. We're going to go into some of the background, talking about barbecue and some of the projects and things I've been building. Then I'm going to do an overview of the architecture, how it has been evolving. Third step, we'll go deep dive on the cloud architecture, see improvements that has been made and changes that I've been doing. And then we're going to round it all up with some summary and last thoughts. But before we start, so who am I? As I said, my name is Jimmy. I'm a father of 2 girls, which makes me afraid of nothing. I'm a IoT, serverless, and barbecue enthusiast. I've been working with serverless since the beginning of 2016. So when I started out using serverless and primarily AWS Lambda had a max RAM memory of 1 gig, and there were no environment variables. So that is how Lambda old I am. I'm an AWS ambassador and AWS community builder, heavily engaged in the AWS community in Nordics. In my daytime job, I work as head of AWS technologies at Sigma Technology Cloud here in Malmö. So let's jump into the background and see a bit about what I've been building. But we need to start with the barbecue parts, of course. What is barbecue? When I talk about, or we talk about barbecue, we talk about low and slow versus hot and fast. So with low and slow, we target to have a low temperature for a longer period of time. And the reason for doing that is to break down connective tissues in the meat, tenderizing the meat, and make it really, really awesome. I normally target the temperature around 120, 125 degrees Celsius in my smokers. There are so many different styles of barbecue. I probably can start a flame war on that one, but I think I will pass. But you have different styles like Texas, Tennessee, North Carolina, UK, Australia, and so on. In Sweden, we tend to lean more towards the US different styles, and then primarily I would say Texas style. When I talk about barbecue with my friends, I normally say that barbecue it's not cooking, it's an art form. Learn how to control your smoker to get the perfect temperature over time. But that doesn't mean we can't use tech, right? So we are all tech savvy, so that's what we do. Different kind of smoker types. Let's see if we can do an audience poll here. Anyone using a ceramic Kamado grill for barbecuing? I see a couple of hands, at least. Anyone using a ugly drum smoker? Oh. Not really, but yeah. Anyone using electric pellet smokers? I see one in the back. Anyone using stick burners, offset smokers, the real deal? Only me? Okay, so this is my smoker. She's a real beauty, right? Sorry? No. This is an offset smoker. This is not ugly. It's really nice. Yeah, it's an offset smoker. It's a stick burner. So let's go over it quickly to see, let you know how it works. Basically, what we do is we put on a fire in the firebox here. And that is how we control the temperature with the amount of wood, meaning the amount of fuel that we use. So more fuel, more heat. That's how we control the temperature. You don't control the temperature in an offset smoker with airflow that you do in like a Kamado grill. Then the heat and smoke travels up here in the food chamber. So that's why it's called an offset. We have the fuel offset. And that little box there is my little ugly IoT thing that I've been building in a plastic container with a Raspberry Pi and some cords. This is an overview picture of the actual IoT device or the that I have been connecting. What I'm using here is a standard 2.5 millimeter food probe. You can buy them at most stores connected to a food thermometer. I think IKEA has a couple of them outside. Maybe you can get one from the booth. They work as a thermistor. So basically, while temperature rise, the resistance increase or decrease. There are two types actually of thermistors. So depending on the type, the resistance in the thermistor rise or lowers with temperature. So let's jump into the architecture, then having a bit of the background of everything. There are two parts here. We have the actual IoT device that's connected on a Raspberry Pi running AWS Greengrass. And that connects to the cloud architecture where we are running serverless things like IoT Core, Lambda, StepFunctions, and so on. So if we start to look at the IoT device itself, it also contains of two different parts. We have the hardware part, that's a Raspberry Pi 4 Model B. I have the 2.5 millimeter food probes, the thermistors I've been showing you. And I'm using an MCP 3008, which is a 10-bit 8-channel analog digital converter. And I use that to convert the resistance readings I get into digital values, and then I can do some math on calculate the temperature. On the software side, I have an AWS Greengrass IoT Core 2.0 running, and I have a custom component that are doing all the mathematical works for me and transmitting the values into the cloud. Initially, when I started this project, it was a pretty basic Python app running on a Raspberry Pi that I then updated using a simple SSH, connecting to the Raspberry Pi, pushing new files and so on. That was a bit cumbersome. Logs was a bit problematic when a math didn't turn out as it should and things like that. So a bit hard to find out all of the different pieces. So let's jump into the cloud part instead and see the initial load on this one. The first draft of the cloud architecture was looking like this. We basically had IoT Core, and we have different rules. With the rules that's sending the messages to different parts of the system. I was sending messages to S3, DynamoDB, and into my business logic. And I guess the little happy man that you see here, that's me, I guess. So there was some lesson learned from this architecture since it was a bit hard to handle. First of all, using IoT Core as a message router was not optimal. IoT Core can do the routing on the MQTT topics, but it can't do routing based on the payload in the messages coming onto the cloud. So I had to send all messages to all different endpoints at the same time, even if that part of the business logic was not interested in that message. And that's due to I couldn't do filtering on the payload. I had to do filtering on the actual MQTT topic. The second part was, since I was sending data directly into S3 to be queried by Athena, every message coming into IoT Core actually ended up as a single object in S3. That produced a lot of small, tiny objects, which is not optimal from a storage perspective, and it's not optimal from Athena and query perspective. So that was not that good. The second part was actually storage itself and the data format. Since I was storing data directly when it came from IoT Core, it basically, the IoT device was dictating the data format for the cloud. So if I needed to change the data format, I actually had to do a new software on the IoT device. And for me, personally, only having one IoT device, yeah, that might not be a big problem, but if you work in an IoT project with thousands or even hundreds of thousands of devices, that's not something you want to do. The last part, the business logic. Business logic was implemented using StepFunctions, SQS, Lambda functions, things like that. And every time I wanted to introduce a new service, a new part of the business logic, I either had to extend my current step function, making it huge, almost looking like a monolith, or I needed to add one more service, and then once again I was sending messages to one more place. I also discovered that several of these business logic services wanted to do the same thing. They wanted to send a message to me when things are happening, which meant that I had started to reuse components and things like that, and suddenly I had a big monolith, which I don't want to have. Now, improvements. Of course, everything can improve, right? So, two parts I wanted to improve. I wanted to improve the IoT device itself. I wanted to make it easier to deploy new software. I wanted to improve the software development lifecycle in some way. I also wanted to do better log handling, so I was able to read the logs off the device. On the cloud side, I wanted to introduce an event-driven architecture to be able to decouple things in a better way. I also wanted to do data transformations, data augmentation in a better way. I wanted to do some proper ETL. I don't want the IoT device to dictate the data format that the cloud need to work on. So, starting with the IoT device, looking at the changes I did to obtain this, I would say AWS Greengrass to the rescue. Greengrass works like this. You run it on my Raspberry Pi, and it comes bundled with a lot of good things from AWS directly. So what I wanted to do is I wanted to interact with other AWS services, not only IoT Core. I wanted to be able to fetch configurations from e.g. like S3, DynamoDB, or something like that. I wanted the device to connect into the cloud and fetch that configuration. That way I could easily change the probes and how they were calibrated. So I wanted them to fetch that. And IoT Greengrass comes with that functionality. I authorize an access to AWS Cloud. It connects and fetches data from Amazon S3. I also wanted to improve the log handling. And with Greengrass, it comes a very good log component built in that's provided by AWS. So with that log component, logs are actually collected on the device and sent up to the cloud in Amazon CloudWatch, which means I can read the logs off the device. Perfect, that's exactly what I want to do. I then rebuilt my own software, created it as a custom component that I could deploy to the Greengrass using the standard mechanism that AWS has built for Greengrass, which meant that I could sit on my computer, do the changes, and just push it via the cloud instead. Cloud architecture, this is the big part, and this is the fun part. This is where all good things starting to happen. The second interaction is started to look like this. Clearly, microservice architecture, I started to break things out. I introduced Amazon Event Bridge as an event engine, moving towards an event-driven architecture. This way, I can pick up the messages from IoT Core and post it. I removed all the rules and kept only one, so all messages coming to IoT Core went into SQS. From SQS, I used the Lambda function to send it into AWS Event Bridge. Now, I really wanted to go IoT Core Event Bridge, but unfortunately, there's no integration points for that yet. So hoping that comes, so I could get rid of this SQS queue. But all the messages are coming into that part. This means that I now can do payload filtering. So I can do the filtering on Event Bridge and can filter on the payloads of the messages. I don't have to stick to an MQTT topic. So, deep dive. Now let's look at the different services and what they're doing actually. When we start here, let's take a closer look at this part, storage first, which is a pattern I really, really enjoy to use and really like. Storage first pattern is basically that you remove processing. So the first thing you do is store your data. You store the data, then you process the data. And you can do that. Doesn't have to be like in this example where you have IoT Core, SQS. It could be like Amazon API Gateway, DynamoDB, API Gateway S3 or something like that. The thing is that you take the message and you use managed services and you store it directly. And as soon as it's been stored, you start to process it. This way, even if processing fails, you still have the data, right? So if you do message directly to a Lambda function fails, you have actually lost the data. So storage first, I introduced that, really good pattern, and I really enjoy using in the cloud in different parts. Next part in the architecture we're going to take a look at is this part here. This is the data augmentation service. So what I'm doing here is I'm using a pattern, data transformation pattern in Amazon EventBridge. So message is coming to EventBridge, goes to the data augmentation service that does its magic and sends a message back to EventBridge. Meaning that that one is the first service that ever touched the data before any other service gets any form of information. What this does, I implemented this in AWS StepFunctions, basically writing no code at all, using all service integrations with StepFunctions. What I can do is I can fetch information like configurations, I can fetch things like the previous data points, and I can augment the event coming from the event from the IoT device and send it back into Amazon EventBridge. So what I'm doing here, actually fetching thresholds, meaning, okay, I have set the threshold, okay, I want to run the temperature in my meat up to like 95 degrees. I want to keep a temperature range in my smoke between 120 and 130, and things like that. I augment that onto the events and send them back onto Amazon EventBridge. So next service on the list here that is basically the fun service, that's where all the barbecue magic happens, is actually this one. So the detection service, that I call it, maybe a bad name, but once again I started to implement it using Amazon StepFunctions and writing as little code as possible. And what this does, as I said, this is where the barbecue magic happens. I detect the thresholds, so I detect if I'm out of range, so if I'm below 120 or above 130 or whatever range I've been setting. And I'm also alerting if I reach the temperature I'm aiming for in the meat. But it does more than that, because that's really basic detection, right? I also want to detect if the temperature starts to drop or rise suddenly. The thing with that is, because if the temperature starts to drop, I know that the fire has gone out and I need to add more. And if the temperature rise too much, too quickly, I know that, oops, maybe I added too much wood. I have to remove something. So I do that, but that's a basic interpolation of the values, so very basic one. And last thing I want to detect is the dreadful stall. And what is a stall, if you don't speak barbecue? That's basically when the temperature in the meat suddenly stops to rise. It normally happens around 70 degrees Celsius, and the temperature just stops. You have had a nice linear curve, and then it stops. And it can actually drop a couple of degrees as well. I want to detect that, because there are two things I can do when I hit the stall. I can either rise the temperature, or I can wrap the meat, or I can also just power through and just keep it going. And you're thinking, what is a stall? What is that? Well, there are, I think, as many theories around the stall and why it happens as there are pitmasters. But there are two theories that I think I like the most, and I think is correct one. One is that at 70 degrees, you start to break down some of the fat. Some of the fat in the meat starts to render, and that lowers the internal temperature of the meat. The second theory is actually that the meat acts as our bodies. So when we get hot, we start to sweat. And the meat does the same thing. It starts to sweat. So there are moisture on the outside of the meat. And for the temperature to be able to keep rising, that moisture need to vaporize. And not until that process stops does the temperature keep rising. But as I said, there's as many theories around this as there are pitmasters in the world. So, but those two I think is a good one. Next part in this architecture is actually the entire architecture itself. And here is when it comes into serverless and event-driven architectures. So why do I do event-driven architecture and why do I do serverless? Well, I wanted to create loosely coupling, so that's a good way to use event-driven architecture, to loosely couple all the services, have them observe instead of just having APIs. Each service can scale and fail independently. Doesn't mean that I don't stand still if, for example, my data storage or notification service goes down. Things doesn't stop. I keep collecting data and everything can come back. And it's really cost effective. I'm running this in a very small scale, so when I'm not using my thing on my IoT device, I don't want to pay money for it. So serverless, perfect, pay what you use. And it's really simple to extend all of this, because if I want to add in one more service, it just adds and it starts listening to events on Amazon EventBridge. I don't have to know about it. I don't have to write a different IoT rule. I just add it onto the EventBridge and the data comes to it. And with serverless, it comes with high availability built in. So, have this thing helped me do better barbecue? Have my barbecue improved? Am I doing great barbecue? I would say it does. So some nice burnt ends, some pulled pork, nice ribs. So yes, I would say it helps a lot to do use technology to improve your barbecue skills. So let's talk a bit about takeaways and thoughts around this project that I want to leave you with. Start with choreography and orchestration. I think they are better together. So in this picture, all of the four boxes are an isolated component that where we can implement our business logic. And in these components, we can use choreography or orchestration. So we're using Amazon StepFunctions. Things need to happen in a certain order, and we can do the business logic in a really simple way using that. Then we in the middle be using Amazon EventBridge, and that way we can route events to different parts, different services, and make it really easy to extend and improve our architecture. So, talking about Amazon StepFunctions, there are two different workflow types when we are using Amazon StepFunctions. One is the standard workflow, and the standard workflow is basically for long-running tasks. So we can run it up for 1 year, and we can do around 2,000 starts per second or something like that, and you pay per transition. So if you have multiple states in your step function, you pay for each state transition. In the express workflow, it's for short-running tasks, less than 5 minutes. You can run a lot of them, like 100,000 invocations per second, something like that. And you pay for runtime. So even if you have 100 state changes, you only pay for the total runtime. And the express workflows is what I primarily use, since I don't need a long-running task. I can do all of my things, all of my mathematical things, and all my barbecue in less than 5 minutes. I'm using express workflow, then I only pay for the runtime. I don't have to care about the number of state transitions. One thing to keep in mind if you build things with Amazon EventBridge, StepFunction, and using an express workflow, which means it's asynchronous invocation, is that for asynchronous invocations, express workflow uses at at least once delivery method, meaning that you can get the same event triggering the express workflow twice. That means that for dev and test, probably not happening, but if you run this in a large enough scale in production, it will happen. So it's really important that the services that you implement using an express workflow is idempotent and actually can handle being sent the same data twice, so you don't do this math twice in a wrong way. So not doing it maybe for a bank, so suddenly you have 2 withdrawals from your from your account since you got the same event triggered twice and you didn't really implement your service to be idempotent. When you're building an event-driven architecture, I strongly urge you to create subscriptions. What do I mean with subscriptions? Even though a rule, an event rule in Amazon EventBridge can have up to 5 targets, I strongly recommend you to use a 1-to-1 mapping. So 1 rule, 1 target. And the reason for that is because if we don't do that, let's say we add 3 targets to our rule, we actually create coupling on the filter. So I create the filter for the event. And now I have created a coupling on the event filter and not on the event itself. And what happens if I add a 5th? What if I need a 6th target? Then I need to create a new rule and I need to keep track of, then I'm going to add it to this target here and all of that. And that makes everything a bit complex. Also, if you need to change the filter, it will impact all of your targets. So if you need to change the filter for one of the targets, it will impact all of the targets. Instead, I recommend that you use a 1-to-1 mapping. That means that we create the coupling on the event itself. Actually, order created, threshold breached, things like that. And then we don't care. Then we create the coupling on that event and not the filter that we are using to send the data to our target. If we need to add more targets, we just create 1 more rule. Yes, we can have a lot of rule in EventBridge then suddenly, but we're using this as infrastructure as code, not a problem, and it's really efficient. And we can change the filters independently. We will never affect any other service running in the system. So strongly recommend that you do subscriptions. In each AWS account, in each region, Amazon EventBridge comes with a default bus. The default bus is what the AWS services use to communicate. Meaning if an EC2 instance is created, a Lambda function is created, there is an event about that being sent on to the default Amazon EventBridge bus. Can you use this bus for your applications? Of course you can. But I would recommend that you don't. Create custom buses for your applications. That way you isolate the data that AWS is producing from your application. And if you're running several applications, you have several buses. That way you can also isolate in each microservice can have its own bus for internal communication if you need that. Otherwise you can leak the business logic onto all other buses. So it's the same reason we don't use a default VPC in AWS. Just leave it alone. Don't touch the default bus. Let that be for the Amazon services. One pattern that I normally say you should do is that you should use AWS Lambda to transform data, not transport data. And what I mean with that is Lambda is not really that optimized to pick up data and just send it to different services. It's like waste. Instead, you should do transportation in a different way. So Lambda should be used to implement transformation, processing, things like that. It shouldn't be used to transport data. In some cases, we can't avoid it since there is no other way to connect different services and introduce a Lambda function. But I still recommend that you try to avoid it. I'm breaking the rule myself, as you see, with this architecture that we're building. I am transporting data right now with Lambda, IoT Core, SQS, Lambda, EventBridge. I could have done it differently. could have done it like this. So having IoT core, invoke an AWS step function, and in the step function I could use the SDK integrations and just take the data using the SDK integration and send it onto EventBridge. That way I'm not using a Lambda function to transport the data. I'm using 100% AWS managed service with a built-in SDK integration to just move the data onto EventBridge. That would of course then lose the storage first pattern, but yeah, you have to choose. So, future and summary then. What's next for this project? And how do we want to improve? What I want to do is I want to add a camera support. That would be really nice. As I said, I want to detect if the temperature starts to drop due to the fire going out. The problem is that, my smoker is 8mm steel. It's really thick, and it retains heat really good, which means that the fire can go out and be out for quite some time before I can see the drop in temperature, since the heat is retained in the steel. So sometimes when I detect a dropping curve, the fire is already out anyway. So I want to add a camera that I can point to the fire and have second notifications onto that, oh, wait a minute, the fire is about to die out even if the temperature is not dropping. That would be really, really nice to add. I want to try and run all of my mathematical functionalities that I have in my custom component on the device as Lambda functions on the device. So instead of, as I have now, a long-running software that just fetch data, pauses, fetch data, pauses, and then transmits, I would see if I could move that into a Lambda function that is invoked on a schedule instead. That would be super nice to get rid of a long-running task, something like that. I want to start experimenting a little bit with machine learning here to see if I can build up some form of machine learning to do better detection of the drops and rises of the temperature. Today I'm just doing basic interpolation and things like that. So adding camera support, adding some machine learning models, I can calculate everything together. It would be quite interesting to try out. And lastly, I want to do an Alexa integration. So today, when I get a notification, I have an SNS topic, and that sends a text message to my phone with information. It would be really nice to integrate everything with Amazon Alexa that I have all around my house anyway, and have a notification go bing, and I can just ask Alexa, hey, what's the temperature, or read me the notification. So then I could use that system instead. That's a summary. We've been talking about how to build an IoT system for barbecuing. We have looked a bit on serverless and event-driven architectures. And we have looked at how to get great barbecue with help of technology. If you're more interested in event-driven architecture and serverless, I am doing one more talk this afternoon where I will go even deeper onto that topic, actually. So with that, I say thank you, and thank you for listening.